Even with all of the controversy that surrounds the life of Werner Heisenberg, there is no doubting his brilliance. The root of this brilliance lay not in his ability to work tirelessly on a problem with almost brute force until it yielded its answers in the style of Rutherford, nor did he intuitively sense when an approach would give the correct results in the way Bohr did. His solutions explicitly avoided trying to visualize an answer in the geometry of space-time as Einstein did. Instead, Heisenberg's brilliance resided in his ability to take risks, to discard ideas that did not serve the goal of describing a system, and then inventing new models that better interpreted or explained the empirical data. It was this ability that Pauli, his most trusted collaborator, most envied in Heisenberg. It was what allowed Heisenberg to develop models and ideas that would lay the foundation for ideas as diverse as electron spin and nuclear forces. Most importantly of all, it led him to put forward the idea that would overturn the cherished philosophical concept of strict causality. His revolutionary intellectual abilities were displayed almost immediately when he joined Sommerfeld's seminar group. From there, on to Göttingen, under Max Born, and then under the mentorship of Niels Bohr, and finally as a full professor in Leipzig, Heisenberg would challenge the established ideas of quantum physics in search of descriptions that matched the empirical data he so prized. Over the course of a single decade, this ability to create and embrace revolution would remake the atom and forever alter the way we look at the world. Hello, and welcome to the Scientific Odyssey. The Scientific Odyssey is a many-part journey into the history and philosophy of science. My name is Chad Davies, and I'm the writer, host, and producer of the podcast, where we consider the ideas, processes, and results of over 2,500 years of scientific inquiry and discovery. Series 2, A History of the Atom. Episode 16.3, Supplemental, The Revolutionary. As we begin, let's take a moment to recap the situation in atomic physics in 1920 as Heisenberg joined Sommerfeld's group in Munich. The model of the atom has really changed from the billiard ball of Dalton. Thomson has extracted the electron from the supposedly indivisible sphere, Becquerel and the Curies have shown that it can emit other particles, and Rutherford has shown that most of the mass is located in an even smaller nucleus made up of at least positive charges. In order to resolve the puzzle of how Thomson's electrons fit with Rutherford's nucleus, Bohr has suggested a peculiar model of the atom wherein the electrons orbit this nucleus but only at specific levels. While this model is extraordinarily successful at explaining the spectroscopic data produced by the hydrogen atom as observed by Kirchhoff and mathematically described by Balmer, it is a strange mix of classical and quantum ideas. The former are borrowed from analogies with planetary systems, with orbits understood to be the path an object takes through space with a specific velocity that results in an understandable change in position. It will be these sorts of models that Born's group in Göttingen will be working with when Heisenberg joins them in 1922. The latter are taken from the work of Boltzmann and Planck, who were the first to think of energy in discrete chunks, but more specifically and directly from the derivations of Albert Einstein, who said that photons could not be fully understood as just waves, but must be seen as packets of energy that came in discrete, quantized amounts in addition to that. Bohr's model was applied to other single electron systems such as helium that had one of its two electrons stripped away due to being in a high energy environment. It was this application that convinced many a skeptic, including Einstein, Rutherford, and the American chemist Lewis, of the model's effectiveness. In 1919, Wolfgang Pauli was able to apply the model to solve the spectrum of the ionized molecular hydrogen. Unfortunately, the model was not successful at explaining the spectrum of regular helium or any other element with more than one electron, nor could it account for the changes in the spectrum of an atom when the atom was in a region of high electric or magnetic field. Out of these problems, had grown a small but significant research community centered on three institutions: Munich, Göttingen, and Copenhagen, with contacts to Rutherford's first in Manchester and then, after the war, at the Cavendish in Cambridge. As was often the case in a field of research-based inquiry, unresolved problems with the description of the system, in this case the atom, creates not a barrier, but rather a group of researchers dedicated to finding solutions. The problems are seen as opportunities to further understand the system being studied through the process of hypothesis modification and experimentation. So, a good question to ask might be why this community arose in Germany at this time. To answer that, we have to look at the broad social picture following the conclusion of hostilities related to the Great War. When the armistice was enacted on November 11th in 1918, the Entente powers put forward the narrative that Germany had been the aggressor in the conflict and that the unfathomable loss of life and destruction of property were to be placed firmly on her doorstep. This narrative was reinforced by the fact that at the war's outset, Germany had invaded neutral Belgium and committed certain atrocities that turned much of the world's public opinion against the nation. This was again reinforced when Germany took up unrestricted submarine warfare in late 1916. While Wilson tried to create a structure that would lead to a more stable Europe, England and France demanded that Germany be excluded in a new post-war power system, a demand that was more or less completely realized politically, economically, and geographically. This ostracization extended to the sciences as well, where German researchers were excluded from scientific conferences and funding for almost a decade following the war. The consequences of this reality in the physics community in Germany were twofold. First, German scientists, and really academics in general, felt that the way in which Germany would be rehabilitated would be through demonstrating that its culture was still on par with that of any other great nation in the world. Specifically, in atomic physics, a majority of the cutting-edge research in this area would be produced by German institutions and German researchers. This production was a great source of pride for Germany as a whole, even if the work was theoretical rather than experimental, and it showed the vibrancy of the nation's intellectual community. The other consequence was a more general retreat from political life in academic centers. After the war, there was a great deal of political unrest throughout Germany that mirrored the struggles we discussed in Munich. The academic class was in a conflicted position in that they wanted a more open and democratic government, but they opposed the growing influence of the communist elements that attempted to gain power from the struggling Weimar Republic. They saw the political and physical strife as something that produced nothing and kept Germany weak, and thus often retreated to their work rather than engage in the factious political debate. While they were able to protect their position in society, this taking leave from the public square would have significant consequences down the road, as ultra-nationalistic elements attempted to gain control of the apparatus of government. For Heisenberg, this was evidenced in his quote-unquote finding a center that summer evening in the castle courtyard. On an intellectual level, he retreated into the world of physics and music, attracted by their abstract beauty and purity. And in the social sphere, the work of leading his Pathfinder group took him into the mountains and fields, far from the right-wing rallies and economic difficulties that plagued the nation. When Heisenberg joined Sommerfeld's group in 1920, he almost immediately showed the daring nature of his intellect in looking at a problem in atomic physics. As I discussed in earlier episodes, the program in Munich was centered on modeling the spectroscopic data being acquired by other groups. Sommerfeld himself had made his name by making corrections to Bohr's original quantum model as required by Einstein's theory of relativity. The issue was that the spectroscopic data being produced for any number of different elements was proving difficult to model. What was encouraging, however, was that the data showed clear numerical relationships, hinting at, as we've mentioned previously with regards to the periodic table, underlying structure that might be able to be modeled. As Sommerfeld wrote, quote, "The musical beauty of our number table will not hide the fact that it represents a number mystery. In fact, I do not yet see any way to a model-based explanation either of the doublet-triple data or of their magnetic influence." Unquote. At this juncture, Heisenberg entered the program and in short order provided a solution to the problem. To do so, however, he had to violate the sort of rules Bohr and Sommerfeld had established in order to mesh the classical picture of the atom with the quantum aspects they had introduced. Sommerfeld had given him the data from the experimental physics group at Tübingen that the professor had begun analyzing with some limited success. Starting from there, Heisenberg worked out a solution that dealt with all of the difficulties Sommerfeld had been stymied by. He did so by assigning half-integer values for the inner quantum numbers Sommerfeld had developed, i.e. giving them values of 1/2, 3/2, 5/2, etc. This solution really demonstrates the willingness of Heisenberg to abandon convention, in this case, integer-valued quantum numbers, in order to make progress. This was the core of his genius, something we'll return to over and over in this episode. The ability to follow the data wherever it took him in building theoretical models, even if that meant he had to throw out previously established ideas. Of course, this willingness to abandon convention wasn't always well received by his colleagues or his mentors. In this particular case, Sommerfeld is said to have exclaimed, quote, "That is absolutely impossible. The only fact we know about quantum theory is that we have integral numbers and not half numbers." Unquote. This was a fundamental tenet of the quantum model. Energy came in individual and equal bundles, or packets, that couldn't be divided further. This idea went all the way back to the initial work of Boltzmann in statistical mechanics and had been developed through the work of Planck and Einstein. The arguments for this model were based on a specific physical understanding of the systems that did not allow for half values, something that had been retained in the Bohr-Sommerfeld model of the atom. The specific of Heisenberg's model, something that was dubbed the quote-unquote core model, and involved the idea of the outermost or valence electrons interacting with the electron structure of the inner closed electron shells in a way that shared or split quantum quantities, is too complex to go into here, but we can make a few comments about it. First, it violated almost every method of careful model building usually used by the Munich, Göttingen, Copenhagen group. Second, as we just mentioned, there was no physical basis for the idea of half quanta or of quantum sharing. However, and this is the most important thing when it came to Heisenberg, the model worked when nothing else did, and so the young man went with it. To his credit as a teacher, Sommerfeld did not squash the idea, but refined his work on the basis of what Heisenberg was doing, even if it didn't make sense or fit the established methodology. This was vitally important in the developing relationship between Sommerfeld and his young student, who had become used to discounting older men who wished to cling to old ideas, whether they be in science or politics. Pauli, a more senior assistant of Sommerfeld's at this time, was not as accepting when he first saw Heisenberg's work in September of 1921. He complained that if someone was allowed to introduce half quanta, then why not quarter, an eighth, and so on? Heisenberg countered that the model worked, and, if that's what the data demanded, then so be it. This was also to be a hallmark of Heisenberg's work. For him, a model didn't have to make physical sense to be considered valid. The more important criterion was that it successfully accounted for the data being modeled. As he would write to Pauli during this time, quote, "Success sanctifies the means," unquote. For Heisenberg, the physical understanding would always follow once the model was shown to produce the correct data. In this case, the physical interpretation that would grow out of Heisenberg's work would be the idea of electron spin. While this didn't exactly match up with his idea of quantum sharing, as the half-integer value for the spin, or intrinsic angular momentum as it was often called, would reside with each single electron, the breaking of the rule of integer values only would allow others to move in new directions that would bring the necessary physical understanding of how the physical system worked. In this case, it would be Ralph Kronig and Pauli who would develop the idea of spin more clearly, and George Uhlenbeck and Samuel Goldschmidt who would do the experimental work to measure the property. What is somewhat remarkable to me is that Sommerfeld didn't tell Heisenberg to make this his dissertation topic. Apparently, the gap between theoretical modeling and physical understanding was great enough that while Sommerfeld would support the publication of the model, he suggested that Heisenberg do his dissertation in a much less controversial area, hydrodynamics. In other words, it was okay to rock the boat in a journal devoted to the most abstract ideas of theoretical physics in work related to a fairly fringe topic, but not so much when trying to get a committee to accept one's bona fides as a reputable physicist at the beginning of a career. And to be honest, this is still oftentimes the case. During this time, another obstacle presented itself as well. It turned out that Bohr wasn't nearly as enthralled by the model as Sommerfeld. This is not surprising given Bohr's intuitive approach to physics, which stressed that both the physical and philosophical aspects of an idea needed to be worked out for the idea to be worth really considering. In his 1922 series of lectures, the Master of Copenhagen would get a chance to take the measure of this previously unknown student of Sommerfeld's. The first encounter between the two men, separated in age by over 15 years, was at the end of Bohr's lecture on what was known as the Stark effect. This term refers to the splitting of spectroscopic lines due to the presence of strong electric fields, as opposed to the analogous Zeeman effect, which involved magnetic fields, and it had been the subject of work by Bohr's chief assistant in Copenhagen, H.A. Kramers. Bohr had commented favorably on Kramers' insights during the lecture, citing a set of mathematical derivations that offered some clues as to how the effect was produced in the atom. Heisenberg was familiar with Kramers' paper on the subject and had already criticized it back in Sommerfeld's seminar group in Munich prior to the lecture series. During the Q&A at the end of the lecture, something that is usually just filled with queries designed to clarify points made during the lecture by other professors in attendance, Heisenberg violated a number of academic protocols by rising to challenge the Kramers' calculations. While Bohr was able to respond to Heisenberg's criticism of the work, he was surprised by it and decided to invite the young man for a walk to get to know him better. It was during this hike to the top of a hill that overlooked the town that Heisenberg first got to meet one of Europe's two greatest living physicists. The impression was immediate and lasting. The conversation ranged over a broad number of topics, including physics and the philosophical issues concerning the atom and how to understand it correctly. This would begin a lifelong discussion that would shape atomic and nuclear physics for years. Bohr's wide-ranging interests were in stark contrast to the focused work of Sommerfeld, who was sort of a quantum technologist. The two would meet again the following morning over breakfast, along with Sommerfeld, to go over the specifics of Heisenberg's model. While the conversation was productive, with Bohr quickly coming to an understanding of Heisenberg's methods and finding no fault in them technically, the two men still remained a far ways apart in terms of their philosophical approaches. This would be put on display when Bohr, in his fifth lecture, specifically addressed the core model. While calling it a, quote, very interesting paper, he then went on to say, quote, it is difficult to justify Heisenberg's assumptions, unquote. This was about as strong a rebuke as Bohr ever expressed in public, and it reflected his belief that theoretical physics was about more than just getting the models right that could explain the data being collected. There had to be an understanding of why the model worked, and what that would mean in broader terms. Moreover, one couldn't just throw out older accepted ways of doing things just because they were inconvenient, at least not without careful deliberation and extensive justification. Still, though, Bohr's diplomatic handling of the controversy would profoundly influence Heisenberg, who would write to his parents regarding Bohr, quote, Bohr is the first scientist who makes an impression as a human being. He is not just a physicist, but much more. With me, he is always especially nice. He always comes to me when he sees me anywhere, and he has invited me to see him once again next week." Unquote. Before you think Heisenberg's gone all fanboy for Bohr, you should remember that he's all of about 20 years old at this point, and the second most famous physicist of Europe is wanting to spend time with him. While Bohr was the kind of man who would go out of his way to take interest in a bright, young man, someone with talent, just as Rutherford had taken such an interest in him, one has to appreciate what an impression Heisenberg must have made on the older man, and the resultant attention must have been like for Heisenberg. I think it'd be something like Tim Cook asking some first-year graduate student from a place like Georgia Tech to have lunch with him to talk about the ideas of human interface design for mobile computing devices, and then talking that conversation up in the next, Mac or Apple Worldwide Developers Conference keynote speech or something. Not long after the Bohrfest lectures, Sommerfeld was scheduled to take a sabbatical year in the United States. During his absence, he worked to find spots for his best students to continue their studies in his absence, and Heisenberg was sent to work with Max Born in Göttingen. Prior to departing to join Bohr's Institute, Heisenberg was able to attend a conference on hydrodynamics in Tyrol, an ethnically German territory that had been given to Italy as part of the post-war reparations. The events surrounding this meeting allow us to take a brief digression into a topic that would come to dominate both German science and Heisenberg's career about a decade after this. While Heisenberg had gotten the chance to meet the second most well-known physicist in Europe, he had yet to meet the man who was the most well-known, Albert Einstein. Einstein had been scheduled to give a series of lectures in 1920 at Munich, just as Heisenberg was just first enrolling into place. However, the lecture was canceled due to a series of circumstances that demonstrated the deeply divided attitudes of German academia following the end of the war, especially in Munich. During the time of the communist government in Munich, during those early days of the Weimar Republic, the workers' groups had specifically targeted the faculty at the university as they represented the sort of bourgeois element of pre-war society. When the pro-government forces expelled the communists, they understandably received a good deal of support from the faculty there, an attitude that extended well beyond the entrenching of the more nationalistic elements in the local government. The most notable outgrowth of this was a tolerance and even encouragement of ultra-nationalistic student groups. When news of Einstein's 1920 lectures in Munich was released, these student groups rallied to protest and demonstrate against the visit. The reason for this opposition was Einstein's Jewish heritage, but more importantly, his outspoken support for the new Weimar government. Because of the uproar, in some cases supported by the faculty, Einstein canceled the lecture, something that was a huge blow both personally and professionally for Sommerfeld. Heisenberg chalked the entire incident up to those who had not had the insight to understand that engagement in the political sphere was not the truth path, his center, and thus wrote it off as an aberration. 2 years later, however, a similar incident happened at this hydrodynamics conference Heisenberg had been invited to present at. Once again, Einstein was asked to deliver an address to the conference, but in this case, the opposition was from a much more significant source. The German physicist Philipp Lenard organized a protest claiming that Einstein's theory of relativity was nothing more than a failed hypothesis that deserved no attention. There was, of course, no basis for this claim. Rather, it was motivated by the just emerging Deutsche Physik movement. This movement held that physics done by racially pure Germans was inherently better and more appropriate than those done by others, specifically those of Jewish heritage. As both the great theoretical advances of the 20th century, relativity and quantum theory, were created and advanced by a number of physicists with just such a background, both subjects were attacked as being flawed. Since Einstein was deeply involved with the creation of both fields, he was often specifically targeted as being a symbol of what was wrong with post-war German science. When Einstein was awarded the 1921 Nobel Prize in Physics, there was a strong backlash amongst those who held this position. Just prior to the conference, apprehension was particularly high due to the recent assassination of the Weimar Republic's Jewish finance minister. Einstein was the frequent recipient of death threats from elements of the ultra-nationalistic movement, and it was feared that he too might be a target. With the promulgation of a flyer at the conference denouncing Einstein and his work, signed by 19 prominent scientists and physicians, it was decided that the great physicist lecture would be replaced by one given by the very competent but less well-known colleague Max van Loo, the Nobel Prize winner from 1914. The flyer was much more troubling to Heisenberg. This time it wasn't a group of uncritical students chanting slogans in the pubs of Munich, but rather acclaimed scientists within the German academic establishment. Leonard was himself a Nobel Prize winner. Heisenberg found the charges deeply troubling, but felt he lacked the position or prestige to effect change. While the incident did make Heisenberg more aware of the issues beginning to shape dialogue in Germany's public square, it would still be a while before he become involved in those discussions. His response to this, though, also demonstrates his willingness to accommodate political persecution in order to remain within the scientific community. We'll return to this theme and develop it further in the third episode of this biographical series when we discuss Heisenberg's involvement with the Nazi regime. After traveling to the conference, Heisenberg went to Göttingen to take up his position with Max Born. In this research environment, Heisenberg's half-integer model was put to the test, as it was still opposed by Bohr in Copenhagen, who was now joined by Pauli. Bohr insisted that all work in the field should be conducted with the original assumptions intact. In order to test this, the two groups, one in Göttingen and the other in Copenhagen, tried to tackle a specific problem with the assumptions that were made from two different angles. Heisenberg had been able to completely solve the problem with the application of half-integer quantum numbers, but he agreed to work within the Bohr group's planetary program to see if another solution could be found using only the assumptions of the classical quantum approach. As the work progressed to completion, it became clear that both approaches' models, the one from Göttingen and the one from Copenhagen, did not produce the data. This failure threw the Bohr-Sommerfeld atomic model into a state of crisis in the summer of 1923. During that summer, Heisenberg returned to Munich to stand for his doctoral dissertation defense. While this should have been a mere formality, Heisenberg had neglected his study of experimental physics, and during the course of the oral examination, he stumbled badly. As a result, while his dissertation received the highest possible marks from the committee, he nearly failed on the basis of this oral examination. This was a huge blow to the young man's ego and resulted in him fleeing Munich as quickly as possible. As I mentioned in an earlier podcast, it was common for individuals in the Central European educational systems who wished to teach at the university level to do an additional year of postgraduate study, known as a habilitation, and then stand for another round of exams. Heisenberg had arranged to return to Born's Institute to complete this final piece of his education, and with the disaster in Munich, he fled to the relative exile of Göttingen to nurse his wounded ego and to put the embarrassment behind him. Now, while all of this was taking place, the German economy finally just completely melted down. The massive inflation that took place destabilized the country, especially in Bavaria, where the nationalists had the strongest influence. While Heisenberg worked with Born during his habilitation year to fine-tune his work and bring it into stunning agreement with the spectroscopic data, the value of the German mark plummeted to 1/1,000,000th its previous value. In November, just as Hitler was being arrested for the beer hall putsch in Munich, Werner circulated the manuscript that would become the basis of his habilitation thesis, a model that seemed to resolve all of the problems with explaining the Folczmann effect. It was well received by the faculty at Göttingen and was recognized as a huge step towards a solution, even though it continued to violate many of the principles Bohr and Sommerfeld had established. Shortly after this, in late 1923, the government in Weimar was able to get inflation under control, thus diffusing further unrest, by issuing a new currency backed by the very land of Germany. As all this took place, Heisenberg worked with other leaders of the Pathfinder movement to determine the role that the organization would play in national politics. As he had done up to this point, Heisenberg counseled that the movement stay aloof from the political events and positions of the time. Werner felt that the group would better serve the nation's youth by offering them a refuge from the transitory turmoil and upheaval until a time when a more permanent solution was found which could be constructively engaged. What is telling in this correspondence with the other movement leaders during this time is that Heisenberg clearly felt that the Weimar government was only to be viewed as a transition from the stable pre-war government, which had destroyed itself and betrayed its youth with its imperial ambitions, and a future government which would banish the problems that had led Hitler and his henchmen to try to take matters into their own hands. While Heisenberg's work was well regarded at Born's Institute, he found it difficult to get past the failure of his dissertation defense. While he wished to publish the work as soon as possible, his father counseled caution. The older Heisenberg's reasoning was that if Werner hadn't been able to assess his own deficiencies in preparing for his dissertation examination, was he really capable of doing so now? To his credit, the younger Heisenberg recognized that a second setback would likely end his career and thus agreed to have his work checked by none other than Niels Bohr before submission to a journal. So, as he was finishing up his fellowship with Born, he traveled to Copenhagen for 2 weeks in March of 1924 to meet the director there. The two met for several hours a day to discuss physics and the general intellectual trends of the day. As the meetings progressed, the topic of conversation focused more and more on the specifics of Heisenberg's work. Bohr had a number of objections, almost all of which were philosophical in nature. In a letter from Pauli to Bohr, Pauli at this point is at Hamburg, dated February 11, 1924, shortly before Heisenberg's first visit, we see the attitude towards Heisenberg from the Copenhagen group. Pauli wrote, quote, "I always feel very strange with him, for he is very unphilosophical. He does not pay attention to the clear working out of the basic assumptions and their connection with the prevailing theories. However, if I speak with him, he pleases me very much, and I see he has all sorts of new arguments, at least in his heart. Aside from the fact that he is also personally a nice fellow, I regard him as very significant, even genial. I was therefore very pleased that you invited him to Copenhagen. Hopefully, then, Heisenberg too will return home with a philosophical orientation to his thinking." Unquote. As the visit wound to a close, Pauli's expectation was fulfilled, as Heisenberg began to see and appreciate the usefulness of Bohr's philosophical approach to doing physics, saying, quote, "His manner of doing physics is very practical. He always attempts at first only progress in the details." Unquote. By the end of the visit, Bohr felt that Heisenberg's ideas warranted additional consideration, and so arranged a fellowship that would bring Werner to Copenhagen for an additional year of work. So, after finishing up his habilitation thesis, as well as papers on ion polarization and his half-integral quantization ideas, along with working on a variety of other projects, he prepared to leave to work with Bohr's group. Prior to his departure, he finally got to meet Einstein, who visited Born that summer and spent some time with the young theoretical physicist. The big project in Copenhagen at that time was something very different than what either the groups at Munich or Göttingen were working on. The American theorist John Slater had brought an idea with him from Harvard to the group as a fellowship student. This idea, known as virtual radiation fields or a ghost field, was combined with something known as a virtual oscillator approach in order to try to deal with the wave-particle duality problem that occupied Bohr's thoughts for quite some time. This idea, known as the BKS theory, was an attempt to create a completely wave-based description of the atom that was much more classical than Bohr's old quantum model, which was now seen to be fundamentally flawed. As we discussed in the episode on the mathematical atom, this approach was ultimately shown to be incorrect by experimental methods, but the fact that it introduced the possibility that certain classical quantities might have to be thought of in a statistically averaged way was to prove instrumental in the work Heisenberg was about to do. It was in this challenging intellectual environment, working with Bohr, Kramers, and Pauli, that Heisenberg made much of the progress towards developing matrix mechanics. Since I've already covered much of that material in 2 episodes on the mathematical atom, I will not dwell on it here, as this episode is already stretching beyond what I'd like. Suffice it to say that the years from 1924 through 1927 were tumultuous on a professional level for Heisenberg, filled with both highs and lows. As an example of this sort of roller coaster of developments, in early 1925, Pauli was able to conclusively show that Heisenberg's core model of the atom failed to truly account for the motions of the electrons. Yet, in 1926, the Scourge of God was able to use Heisenberg's half-integer idea, along with the matrix mechanics methods he developed with Born and Jordan, to come up with the concept of spin and the exclusion principle. During this time, one can see both Heisenberg's deeply competitive nature and his intellectual daring work to produce models and techniques that broke with the past in just the right way. His abandonment of invoking unobservable quantities, his willingness to generalize the classical ideas of position and momentum and then understand that they did not obey the rule of commutativity, and his tendency to stick with his ideas when in conflict with Bohr, enabled him to push ahead with the interpretation of quantum theory in the face of nearly universal opposition at the time. Moreover, his ability to go back and rework his explanations in order to make them more understandable and more accessible was vital to winning over much of that opposition to his side. At the conclusion of the 1927 Solvay Conference, the Copenhagen interpretation was widely accepted by the participants. By the end of 1928, it was the de facto understanding held by most all physicists outside of the small group attached to Schrödinger and Einstein. As Heisenberg was putting the finishing touches on his paper clearly stating what we now refer to as the uncertainty principle, though a better term might be call it the indeterminacy principle, he was offered the chair of theoretical physics at the University of Leipzig. This was the realization of a lifelong goal, not just of his, but of his family's as well. He was the youngest full professor to be appointed in Germany, and he, along with Peter Debye, turned the physics center there into a world-class institution to rival both Munich and Göttingen. He continued his collaborations with both Bohr and Pauli, who had just been named to the professorship of Zurich in the same year. The work he focused on there was in 3 broad areas. The first was to extend the description of quantum mechanics to incorporate relativistic effects along with the coupling of the wave behavior of light quanta. This problem turned out to be a very difficult one in which he made a number of initial contributions before running out of steam. These frustrations forced him to return to dealing with applications of quantum theory to problems yet to be treated. In these areas, he and his students soon found solutions to electron conduction in metals and the reason certain materials, known as being ferromagnetic, are able to hold a permanent magnetic field. The second was in fostering a conversation on the philosophical implications of the uncertainty principle and Bohr's principle of complementarity. His most influential talks on the subject were given to what is now known as the Vienna Circle, a group of philosophers centered in the Austrian city who were strongly given over to a picture of scientific inquiry known as logical positivism. His challenging of the ideas of Kant and strict causality ignited discussions in coffee houses and smoking clubs all over Europe. The third area of research was to try and understand the nucleus of the atom. Once again, in this field of research, it was his daring intellect and willingness to go beyond the accepted ideas and frameworks of thought that netted him great progress. Beginning in 1931, he started working on what was to be known as an exchange model that allowed 2 electrons in a system to swap positions in an atom without changing that system. While he knew that Rutherford's model of the proton-electron pair in the nucleus had to be wrong, as the restriction on the position of the electron in the pair would violate the uncertainty principle, Heisenberg still started work on a model that would incorporate them. When, in 1932, Chadwick discovered the neutron, Heisenberg was able to incorporate the new information into his work and publish a model that would form the foundation of all nuclear physics to follow. In a series of 3 tremendously important papers, he put forward an idea of two new interactions that would help explain both what caused the nucleus to remain together and why it would undergo beta decay. The 5 years between the end of 1927 and the end of 1932 were productive and fruitful ones for Heisenberg on both a professional level and a personal one. Along with Pauli and Paul Dirac, he established the basis of almost all of the research that was to follow in atomic and nuclear physics. He moved into the well-connected social circles of Saxony, making friends and developing relationships that would prove invaluable later when things weren't so good. He gathered around him a talented group of both assistants and students at a theoretical institute that was the envy of many universities both in and out of Europe. He was a sought-after lecturer and a respected, almost revered researcher. But not all was well in Germany as 1932 drew to a close, and the political world Heisenberg had worked so hard to avoid or shut out would begin to intrude more and more, pushing him further and further off his center. In our next episode, we'll look at the rise of the Nazi Party in Germany, the effect its politics and political ideology had on science, and Heisenberg's role in and relationship with a government bent on setting the world aflame. So until then, full sails on your journey.